On December 23, 2025, a Beechcraft K35 Bonanza, registration November 9540 Romeo, crashed near Pole Butte, Oregon, and the pilot did not survive. There's been a lot of discussion since then. Was this an issue with the VTOL design of the aircraft? Was it weather-related, or was it something else entirely? This is William, and welcome to Black Box Analyst. When people hear the word weather, they often think of storms, heavy rain, or icing. But in this case, the most important factor to understand isn't precipitation, it's wind. The data available for that day shows strong, widespread winds aloft across southeastern Oregon, right at the altitudes this aircraft was flying. This wasn't a narrow band of localized weather. It was a large-scale wind pattern affecting a wide region. Strong winds like this don't just push an airplane along. They create energy in the atmosphere. That energy shows up as mechanical turbulence, wind shear, and, in terrain-heavy areas like this, mountain wave activity. East of the Cascades, airflow can become especially complex. Winds accelerate over ridges, sink rapidly on the downwind side, and form turbulent rotors closer to the ground. What's important to understand is that none of this requires thunderstorms or icing to become hazardous. An airplane can be in clear air and still experience violent changes in airflow. The controls remain connected, the engine can be running normally, and yet the workload on the person flying the airplane increases very quickly. This matters because wind-driven turbulence doesn't give you the kind of visual cues people expect. There may be no dark clouds ahead, no obvious line on radar to avoid. The air itself can be unstable and unforgiving. So when we talk about the environment that day, it's accurate to describe it as hostile, not because it looked dramatic, but because the amount of wind energy present left very little margin for error, regardless of aircraft type. And that's a key point to keep in mind going forward. Bad flying weather doesn't always look dramatic on radar. Sometimes, strong wind alone is enough. Now, let's look at the flight itself, because this is where the available data becomes especially useful. The aircraft departed Susanville, California, and tracked north toward Oregon. Early in the flight, everything appears fairly typical. The airplane climbs into the 12,000 to 13,000 foot range and settles into what looks like a cruise phase. Terrain clearance was not an immediate issue at this altitude, but when we look closer at the tracking data, something stands out. The ground speed fluctuates dramatically. At times, it's quite high. Then, within a short span, it drops sharply by tens of knots before increasing again. These swings happen without large changes in altitude. That's important. If an airplane is flying at a relatively steady power setting and attitude, its true airspeed doesn't suddenly drop in half. When you see large ground speed swings like this, it's a strong indicator that the airplane is moving through areas of rapidly changing wind, strong headwinds, tailwinds, or shear layers stacked close together. In other words, the airplane isn't just flying through the air. The air itself is moving, and it's moving unevenly. As the flight continues and approaches the Pole Butte area, the track geometry begins to change. The path tightens. The airplane starts turning more sharply. The altitude begins to decay, and the speed becomes less stable. This does not resemble a planned descent or a routine maneuver. It doesn't look like a smooth diversion or a controlled letdown into calmer air. Instead, the profile appears reactive, as if the airplane is responding to conditions rather than following a pre-planned sequence. It's also worth noting what this data does not show. There's no clear signature of a sudden engine failure. There's no abrupt, clean break in the data that would suggest an immediate loss of power followed by a controlled glide. There's also no indication of a deliberate maneuver to a specific landing area. What we see instead is a gradual loss of stability. Speed, altitude, and direction all become harder to hold at the same time, and that combination is important. When multiple parameters start to drift together, it often points to rising workload. The effort required just to keep the airplane stable increases, and the margin for recovery shrinks. So based on the flight track alone, this looks less like a single sudden event and more like a situation that became increasingly difficult to manage in challenging conditions. Before we wrap this up, we need to talk directly about the VTOL, because for decades, it's been at the center of a lot of assumptions whenever a Bonanza is involved in an accident. It's understandable why people focus on it. The V-tail looks different. It combines the elevator and rudder functions into two angled surfaces. And historically, that difference became associated with a reputation that still follows these airplanes today. But it's important to separate reputation from reality. The V-tail does not remove any control axis. Pitch and yaw are still fully available. The controls are mixed mechanically so that when you command pitch or yaw, the appropriate combination of movement happens at the tail. From a certification standpoint, the airplane must demonstrate full controllability, stability, and structural integrity across its approved envelope, and the Bonanza does. So when people say the V-tail is harder to control, what they're often describing is feel, not capability. The Bonanza is a high-performance airplane. It's fast, clean, and responsive. Small control inputs produce noticeable results. In smooth air, that makes it efficient and precise. In turbulence, that same responsiveness can increase workload, especially if the air is moving the airplane faster than the pilot can comfortably damp out those motions. That's not a flaw. That's a characteristic shared by many high-performance airplanes, including plenty with conventional tails. Another misconception is that the V-tail somehow becomes less effective in turbulence or wind. There's no evidence of that. Turbulence doesn't selectively affect tail designs. It affects the entire airplane, wings, fuselage, and tail together. If the air mass itself is unstable, no tail configuration makes an airplane immune to that. What does matter is how much margin the pilot has to stay ahead of the airplane. In strong turbulence, especially in areas with mountain wave or shear, workload can rise very quickly. You're correcting pitch, roll, and yaw while airspeed changes, vertical currents push you up or down, and visual references may be limited. If that workload exceeds what one person can manage comfortably, control can begin to degrade, not because the airplane is uncontrollable, but because the situation is demanding. And this is where history plays a role. Early Bonanzas entered a general aviation world that didn't yet emphasize structured transition training for high-performance aircraft. Many pilots moved into them from much slower, more forgiving airplanes. When accidents happened, the airplane's unique appearance made it an easy target for blame. But when you step back and look at loss of control accidents over time, you see very similar profiles in airplanes with all kinds of tail designs. So when we look at this accident, it's important to say this clearly. There is no evidence, based on the information available right now, that the V-tail caused or contributed to this crash. What the data does point toward is a challenging environment combined with a high-performance airplane operating in air that left little margin. That's a human factors problem, not a design defect. Focusing too narrowly on the tail risks, missing the real lesson. And the real lesson is about respecting conditions that can overwhelm any light aircraft. At this stage, this remains an early analysis. There is no official report yet, and investigators will be looking at many factors we simply don't have access to right now, including detailed weather briefings, aircraft condition, and additional data sources. What we can say is this: the environment that day was demanding, the flight track shows growing instability, and the situation appears to have evolved rather than happening all at once. That doesn't tell us why control was lost, but it does help us understand how a flight can become unrecoverable without a dramatic failure. As always, restraint matters. Conclusions should wait for the official investigation. But there is a takeaway worth holding on to even now. This accident reminds us that airplanes don't have to fail for a flight to be lost. Sometimes, the margin simply disappears faster than anyone expects. If you have thoughts or questions, feel free to share them in the comments, thoughtfully and respectfully. And if you'd like to follow along as more official information becomes available, consider subscribing for future updates.